Today, we're diving into one of the most fundamental challenges in all of artificial intelligence. We call it the Goldilocks problem.
I mean, have you ever stopped to wonder how an app can just know the price of a house in your neighborhood? Or how it recommends a movie that you end up absolutely loving? It all comes down to prediction. These systems are constantly digging through massive piles of data, past house sales, every movie you've ever watched, and they use it all to build this kind of digital brain that tries to understand the world. And that digital brain, that's what we call a model. It's the AI's best guess at how reality works. But here's the catch, and it's a big one. Getting that model to be genuinely smart and not just some super-powered memorizer, well, that is incredibly tricky. It's the ultimate balancing act.
And that's what brings us to the heart of this whole thing, the Goldilocks problem. Yeah, you know the story I'm talking about.
See, just like Goldilocks and her porridge, a good AI model can't be too simple and it can't be too complex. It has to find that perfect, just right balance to actually be useful. So what happens when it gets that balance totally wrong? All right, let's start with the first big mistake, making things way, way too simple. This is our too cold porridge. In the world of AI, we call this underfitting. Well, imagine trying to explain the entire plot of a super complex movie using, say, just 3 words. You'd miss everything important, right? The whole story would be lost. That's exactly what's happening with an underfit model. Okay, take a look at this. This graph from a study on gopher tortoises shows the problem perfectly. Each dot represents a tortoise, how big its shell is versus how many eggs it lays. And you can see, it's pretty obvious, the dots follow a curve. But our model? It's just a straight line. It's just too simple. It completely misses the real story here. So, to put a pin in it, underfitting means the model is just too simple to grasp what's really going on in the data. It's not just a little bit off, it's fundamentally misunderstanding the core pattern. It's like trying to measure the curve of a circle with a straight ruler. It just doesn't work. All right, so that's one side of the coin. Now let's go to the complete other extreme. This is our too hot porridge. This is the model that tries way too hard. We call this overfitting. You'd think that adding more complexity is always a good thing, right? More details should mean more accuracy, but as you're about to see in AI, that can backfire spectacularly. And here we go. This graph shows you exactly what goes wrong. Just look at that line. It is frantically twisting and turning to hit every single data point perfectly. It's not learning the general trend anymore. Instead, it's basically memorizing every random little blip in the data, what we call noise. It's become completely obsessed with the tiny details of the data it's already seen. And that is what makes overfitting so sneaky and so dangerous. On the data it was trained on, it looks like a perfect A+ student. It aces the practice test. But the second you give it a new question, new unseen data, it just completely falls apart. Why? Because it never actually learned the concepts, it just memorized the answers. So we've got too cold and too hot. How in the world do we find that just right balance? Well, the secret recipe involves understanding 2 competing forces, and those are called bias and variance. So first up, bias. Think of bias as the error you get from a model's simplifying assumptions. Basically, it's the error from making things too simple. Our straight-line model for the tortoises, that had high bias. It made a rigid assumption that the relationship had to be a straight line, and it was wrong. High bias, that leads directly to underfitting. And on the flip side, you've got variance. This is the error you get from a model that's too complex, too sensitive. It pays attention to every little fluctuation in the training data. High variance, that's what leads to overfitting. This target analogy is just a fantastic way to visualize this. Okay, let's look at the targets. High bias is on the bottom. See how the shots are all clustered together, but they're way off the bullseye? That's consistently wrong. Now, high variance is on the right. The shots are just all over the place. They're scattered everywhere. What we're aiming for, the goal, is that top left target, low bias and low variance. All the shots are clustered right on the bullseye, accurate and consistent. Okay, so let's tie this all together. Underfitting our too cold porridge, that's a problem of high bias. The model is simple, consistent, but consistently wrong. Overfitting the too hot porridge is a problem of high variance. The model is super complex, it's all over the place, and it's chasing after meaningless noise instead of the real signal. Which, of course, brings us back to the whole point of this. The goal of pretty much all of machine learning is to find that sweet spot, the just right model that perfectly balances these two types of errors. And here it is, the just right model for our tortoises. Look at that. You can see how it captures the general curve of the data just beautifully, but it's smart enough to ignore the little random blips. See how it doesn't hit every single point? That's a good thing. This model has actually learned the pattern. It hasn't just memorized the data. So this graph really brings it all home. Let's build it out. As our model gets more and more complex, the bias, that's our blue line, goes down. Great. But at the very same time, the variance, the red line, starts to creep up. The total error the model makes is a combination of both of these, and it creates this U-shaped curve, the green line. And where's our just right model? It's right there at the very bottom of that U. That's the sweet spot, the point of lowest possible total error. Because at the end of the day, this is what it's all about. A model is only truly useful if it can take what it's learned and apply it correctly to brand new situations it has never ever seen before. That ability to perform well on new data, that's the holy grail. We call it generalization. And here's why all of this really matters in your daily life. Let's think about that movie recommender again. An overfit model has just memorized your viewing history. It's going to recommend The Avengers too because you liked The Avengers. But a just right model, an optimal one, it has learned the types of stories you like, the actors, the directors, and it can surprise you. It can help you discover a new favorite movie that you've never even heard of. That's the difference. So the next time your phone's app makes a prediction that is just surprisingly good, you'll know what just happened. Under the hood, it just performed this incredible balancing act. It found the perfect recipe, not too simple, not too complex, but just right. It navigated that bias-variance trade-off to give you something genuinely useful.